All right, welcome to part 4 of 6. Yes, I think part 4 of our discussion on thermodynamic cycles. This is high time for us to finally discuss the second law of thermodynamics. This is why I said in the beginning that we want to know, or we want to study thermodynamics so that we understand our limitations in this physical world. It feels like out of the 5 topics that we have discussed so far, it feels like anything is possible. But there are just some things that are impossible. Right? So what are we going to discuss about? Well, let's dive into the second law itself, right? And it's something that we've already been saying out loud for a lot of times, right? For many cases, we have always said that heat always flows from hot to cold. Essentially, that is one way of saying the second law of thermodynamics, right? Heat always spontaneously, and this is a very interesting, a very important distinction, right? Heat always naturally or spontaneously flows from higher to lower temperatures. We've seen this be broken earlier, but in this case, we know that in this case we are saying spontaneously, without any aid, without any external aid, it will always flow from higher to lower temperatures, right? Natural processes, again, natural processes, right? Natural processes always occur in the direction of increasing entropy. What that means is, right, for a lot of people, you have seen this be written out many times in your textbooks or in many kinds of other reviewers. You will always see this: delta S is greater than zero, right? And the thing about this is that maybe it's just written down as delta S is greater than zero for most of the time, right? But I would like to clarify that it is the entropy of the universe. If literally you were to think about everything ever and put that under, right, as your system boundary, you will always have increasing entropy, right? You might say, well, I've seen a couple of instances earlier wherein we saw the entropy of something decrease. And well, you are definitely correct in there. Right? Say for example, in this case, look at process 3 to 1, right? Your process 3 to 1 has decreasing entropy, right? So what? Is that does that mean that we have just plain and simple we have disproved the second law of thermodynamics? Of course not, right? Say for example here for state 2 to 3, or for process 2 to 3, you can see in here that there's going to be a rejection of heat, right? This is your QR. In this case, is the second law broken? No. It's because this system is not the universe, right? This system is not the universe. And basically what happens is that there is surroundings, right? There are still the surroundings that count, right? And in that case, well, in here, even if your system's entropy decreases, you'll always see, right, your surroundings is entropy, right? Your surroundings is entropy to be higher. If anything, the perfect, or rather the kind of process that would make everything just stay the still would stay still would be an isentropic process. In that case, entropy would not increase or decrease, it would just remain the same. But that is the best we can do, right? The universe will always tend towards higher values of entropy, right? And so, if you're a little bit intimidated by the math speak in here, let me provide a little visual aid, right? Whereas the first law dictates what is allowed to happen in real life in real life processes based on energy, the second law dictates what most likely will happen based on entropy. Right? The first law is basically an equation. So long as all of the numbers are correct, you're going to be good. The second law, however, is a suppose let's think about this in terms of problem solving. Your first law is just you computing, making sure that the math is correct. The second law is you reality checking yourself. Is this going to happen in real life? That is what the second law is saying. And it reality checks, it performs this reality check based on entropy. Your entropy is always supposed to increase. That is what the second law says. And so you might say, okay, I still don't get it. Well, this is the visual aid now. Say, for example, you have a cup of coffee right here that is hot. Right now, mine is what? Lukewarm. And so in this case, let's say that the hot coffee is at 90 degrees, right? And let's confine this coffee to be the system. Don't worry about the steam flowing out. I'm only saying that, or rather, I only added that because, well, I wanted you guys to understand that this coffee is hot. And because it's hot, we can now say that the surrounding temperature is going to be, or rather, besides that, right, we can also say that the surrounding temperature, we can assume that to be a little bit constant, right? Just like what we were doing in Newton's law of cooling. If you guys remember that lecture from before, say for example, the temperature. Oh, sorry. By the way, the temperature now is 27 degrees. So thank you to my air conditioning for that. Say for example, it's 26 degrees. Okay, right? I'll be a little optimistic there. What will happen is that, of course, heat will flow outwards. Right? Heat will flow outwards at, say, for example, 120 units. I'm not going to specify what units these are, right? Maybe they're kilowatts, maybe they're kilojoules, maybe they're horsepower for all I care, right? But in this case, okay, right? The thing about this now is because your heat is flowing outward, you're going to have a loss in energy. Because this cup of coffee is not moving, there's going to be no change in potential and kinetic energy, right? It's not moving up or down, it's not moving around, right? So the only thing, or rather, the only kind of energy it will lose is internal energy. This is a closed system, so this will be delta U. Someone will take offense to this, right? This is the first law because it's saying, wait a second, the math is not adding up, right? You are losing 120 based on your heat, but your loss in your internal energy is only 100. So how can that be? And so we admit this. We say, I'm sorry, right? Oops. Oh no. Let me. Where were we? Oh, this one here. And so, where were we, right? We say, we admit the mistake. We're saying, sorry, okay, it should be 100 here, right? Now, the first law, as a law that only checks the numbers, right? It's going to be very happy. It's like, okay, all right, you've passed my test. It's all right. So now I will present a counter, another example wherein the first law is going to be happy. Another example is, what if the heat, instead of flowing outwards, will flow inwards? Say, for example, if this heat were to flow inwards, your heat would be at 100 at a rate of 100. And so that means that if it's going to flow inwards, your internal energy will now increase. Now increase to plus 100. Notice the first law is still quite happy, right? You say, it says, well, the equation is good, the math is good, I'm satisfied. Someone else is not, though, and that is going to be the second law, because now you think about it. Wait a second, heat is flowing from a cold place to a hot place, right? That is why it is now complaining, right? That is what the second law does. So it is a kind of a reality check. Even though all of the math is correct, this will not happen, right? This will not happen. Of course, there's a big asterisk in there because, well, technically it can happen. It's just very, very, very improbable. Right? For the people who want to know why that is true, you can dive into statistical thermodynamics. But I have a good feeling you guys will not, because adding statistical to something is it's not very inviting for us mechanical engineers at the very least. But anyway, another manifestation of the second law that we're going to discuss now is this for power cycles, right? For power cycles, say for example, you give it some heat, right? You give it some heat, a power cycle will then produce work, and then your QR will be, right, well, waste. Right? Say for example, your QA in here, the amount of heat you have added is 100 units. The amount of work that you're going to get in this situation is going to be 30, which means your waste heat, the heat that you reject, is going to be 70. In this case, let's think about it. What is the thermal efficiency of this thing? Thermal efficiency is output over input. Your output is going to be your net work. Your input is going to be your your input heat. So it's 30 over 100 or 30%. Okay. But if we switched QR and WorkNet, or rather the values for QR and WorkNet, what if now instead of QR being 70, WorkNet is 70? So you're saying, okay, WorkNet over QA is just 70%. Actually, someone's already starting to question this result, right? And the thing about this is that if all of the what do we call this? If all of the work is now all of the heat, right? Basically, if there is no waste in this case, you would say, "Oh, great, that's amazing, right? That's a thermal efficiency of 100%." That's that's going to be a big problem because technically that's not supposed to happen, right? Who said so? This guy said so. This is William Thomson, or he is more known as Lord Kelvin, right? He is one of the lords in the House of Lords back then in the UK. And well, he was also one of the founding fathers of thermodynamics. So basically, someone from the nobility looking at science. Very interesting. Okay? And along with this guy, Max Planck, you may have heard of him if you're. I don't know if he appeared in Oppenheimer, but yeah, he's the founding father of quantum theory. Uh, well, I forget. I mean, I haven't watched the movie, but like I don't remember if there were any appearances that are attributed to Max Planck. But you might notice, well, this guy, he's a little bit too handsome for for science. Isn't he supposed to look like a mad scientist? Well, now here he, yeah, there you go. Right, that's a more scientisty way of looking at Planck. Right. The thing about these guys, these two people, is that they have, right, collectively stated the Kelvin-Planck statement. The Kelvin-Planck statement is a restatement of the second law, which basically says it is impossible to create a cyclical heat engine, or, in other words, a power cycle that fully, is the word now here, that fully converts input heat all into mechanical work. And so what they're basically trying to say is that this kind of cycle wherein your heat input is 100% going to go into your net output is wrong. It is impossible. And the second law is happy because you recognize the impossibility of this, right? And basically the Kelvin-Planck restatement, the Kelvin-Planck statement basically asserts you must have waste. If you want to think about this another way, heat is a very low quality source of energy, right? It's a low quality source of energy because, well, it's for the lack of a term, it's a spray and pray. Like you have heat and you can basically apply it everywhere. Work, however, is a little bit more organized, and in that case, if your device, right, if your device can turn all of that low quality energy into high quality energy, that's going to break a rule, right? There must be some waste that is generated because of this power cycle, right? And so that is the second law through the Kelvin-Planck statement, right? Another thing that is related to the second law, right? Another kind of limitation that is now imposed on us is going to be through this guy. Right? This guy, very handsome. He is Nicolas Leonard Sadi Carnot. He is the father of thermodynamics, right? And it's quite sad. He died at 36 years old, right? He's a French physicist and a military engineer. He was first interested in thermodynamics because of engines, right? And it turns out he was able to be the founding father of thermodynamics, if you want to think about it this way. right? And not only was he one of the first people to think about thermodynamics, about the motive power of steam, that was a book that he published, or that was a piece that he published, right? He was also able to create the cycle. The Carnot cycle is perhaps one of the simplest but also the perfect thermodynamic cycle. And if we remember from Oddball Rex, that is the C in Rex, this is an external combustion engine, and its code is TSTS or STST, really doesn't matter so long as it follows the cyclical pattern. This will be an isothermal, isentropic, isothermal, isentropic cycle. I might say to yourself, wait, where are the steady flow devices? The Carnot cycle does not need steady flow devices because, right, it will be performed in our best friend, this, the piston cylinder assembly. You will have here a fluid, which most usually is a gas, right? Is something like no, actually, no, never mind. It's for Stirling cycles. A fluid, in this case, usually a gas or maybe an ideal gas if you want to, right? And you will have here walls, adiabatic walls, right? These adiabatic walls, from the name itself, they do not let heat transfer to or from the cylinder to these things, the thermal reservoirs. Right? You have these thermal reservoirs, one that is cold and one that is hot, right? And now we can try and start our analysis of the Carnot cycle. We will have not only one, but two diagrams to help us out. We will have the PV and the TS diagram in here. And I recommend, if this is your first time watching, just focus on one side or one diagram for now. Right? The next time you're going to watch this cycle, please focus on the other side. Okay? Now, what we will have here, right, are two thermal reservoirs. So in the TS diagrams, it's going to be really easy to graph, right? The high side is just going to be a line, and the low side is just going to be another line. But in this case, for the PV diagram, isotherms, or basically lines of constant temperature, are going to be graphed as, right? Oops. What happened? Okay, where were we? Okay, spoiler. Just remove that. Okay, I don't know how to invoke that again, right? But isotherms are going to be graphed like what? Okay, yeah, I don't know. I don't know how the fine. Okay, they're going to be graphed using curves like that, and actually those curves are reminiscent of y equals k over x curves, right? If we imagine this as the x axis and this as the oh, so if I draw anywhere a little bit on top, right? Yeah. Okay, very interesting. Yeah. Y. If that is the y-axis, then these curves are going to be right like that. And right, the higher the k in here, the farther away they are from the origin. So that is how we're going to draw these lines, these isotherms. As you can see, this is your high side temperature and this is your low side temperature. Okay. Now that hiccup is over, let's start and graph this fluid. Currently, this fluid has an orange hue, which is a reminder to all of you that this has a high pressure. Oh, sorry, this has a high temperature, pala rather. Let us draw it here. This is going to be our state one. Okay? State one is here. And now what will happen is that this is a high pressure, high temperature, right? You can see that it is a high pressure kind of state right now. It's also at the high temperature line and it's now ready to receive heat. How is it going to receive heat? If you read from earlier, it's going to receive heat isothermally. What you will do is now then let go of the adiabatic wall, raise the adiabatic wall, and now it will transfer heat, right? It will transfer heat, or rather, the thermal reservoir will transfer heat to the inside or to the inside of the fluid. So you're saying, wait a second, this is isothermal, right? T1 is equal to T2. How can it do this? This is actually why right? This is actually why the Carnot cycle is known to be impossible because, well, what is this, right? What is going to be this state, right? State 2 is going to be a hotter, quote unquote, a hotter version because you're transferring heat to the fluid, right? But the thing is, it remained, or rather, the temperature of this thing remained constant. And the reason why is normally, again, right? Normally, heat will not be transferred unless there is a temperature difference. The reason in here why this is going to be transferred in anyway, right? The reason why this is going to be transferred is that this TH right here in this thermal reservoir is just a little bit higher, just a little bit higher in temperature than your fluid. So that's why there's still, right, some heat transfer, although it will happen at an incredibly slow rate. This is also why isothermal processes usually are not followed in real life, because look at this. This is incredibly slow. Okay. And what will happen to it is that its volume will increase. Note what happened in here, right? This is going to be read from left to right. So this area right here is going to be positive. There is a corresponding expansion. Okay. And now what will happen in here? Because of the, say, for the lack of the term, for the lack of a better term, vuelo, because of the vuelo, right? Because this gas is expanding anyway, this is now ready to expand even more and exert work when you lower the adiabatic wall. When you now lower the adiabatic wall, right, the heat transfer stops, but the thing is, it will keep going. This piston will keep on expanding until it's at a point where it is now lower temperature. If you remember from before, right, if you're going to compress a fluid, its temperature will increase. So conversely, right, if you're going to expand a fluid, you will then decrease its temperature. So when you lower that adiabatic wall, it will continue expanding, and it will now expand up until a point where you will be, or rather it will be, at a lower temperature. At TL, you will then say this is now my state 3, right? Notice that in this case, this is an isentropic process. Note that there is no heat transfer going on either from the low side or the high side temperature, right? Or the low side or high side thermal reservoir. So in this case, it is just the piston doing its job until it stops, right? Until it stops. Right? What will happen is that there is going to be a work of expansion. Look at this, right? This is going to be your work, right? That is still positive. And now this is your state 3, right? Note that your state 3 is now at the low temperature. And well, what we will now do is that this low temperature gas is ready to reject heat. Note that in this case, this has a lot of volume. And so if we're going to throw up this side of the adiabatic wall, what it will now do is that it will reject heat to the low side. Just like before, this is going to happen isothermally, right? This is going to happen isothermally. And again, look at this, right? Both of their temperatures are the same. The reason for this, why this is going to still happen, is because it will just have a little bit of a temperature difference to allow for this kind of heat transfer, right? What will happen as well is that this amount of work, right, you are just slowly pushing on the piston so that you can guide this heat transfer to the lower thermal reservoir. This is now your state 4. And now notice we will close off this cycle, right, by keeping on compressing it. Right? If we now lower our adiabatic wall, if we continue to compress it, we will now get it back to its original state, state 1, and now we can perpetuate the cycle. So this is how a Carnot cycle is. This is how a Carnot cycle operates. Okay, so notice that the PV diagram is a little bit too wonky, right? The TS diagram, however, is immaculate, right? It's just a rectangle. And that is because, well, we are taking advantage of the fact that it really is two isentropic processes and two isothermal processes. Okay? So now, in this case, we can think about the input and the output of this power cycle. In this case, your heat added, your input is a rectangle. And if you notice, the height of this triangle, the height of this rectangle is going to be TH, right? Look at this. This is going to be your temperature reading, which is TH. Okay. What about this thing, right? The thing is, this you can just call, well, you can just call that delta S, right? Your change in enthalpy or entropy from state 1 to 2 or state 3 to 4 is going to be the same. This is going to be QA is equal to TH times delta S. This is literally just a rectangle. On the other hand, if you're going to now think about the output, right? Your heat net, or in this case, you can also think about it as the work net because of the first law for cycles. You can also see that the network is another rectangle. That's going to now be, right? That's now going to be delta S, right? This is still the width, but now you're going to take the temperature difference of the high and low temperatures. Excuse me. And so now we can get the thermal efficiency. Okay, if we take the ratios of these two areas, right, note that of course your work net will be just a little bit smaller than your QA. You will get your thermal efficiency. And now let's try and compute for that. Let's remember our work net and QA formulas in here. What we will get is eta TH is equal to TH over TL times delta S, TH minus TL times delta S. And then all over TH times delta S, what you can do is cancel the delta S's. What you will have is TH minus TL over TH. Or, in this case, the thermal efficiency of a Carnot cycle is always going to be 1, right? Because you can divide this, right? 1 minus TL over TH. This is your thermal efficiency. And you might say to yourself, okay, why are you putting it in violet? Why is does this sound important? Yes, because, right, what we will have after this is Carnot's theorem. Right? Carnot's theorem basically states that the thermal efficiency of any power cycle cannot exceed that of a Carnot cycle working under identical thermal reservoirs. What do you mean? Right? So this means that the Carnot cycle is the perfect cycle. But in that case, wait a second. This is not going to give us 100%. So what gives? Yeah, that's exactly why when I first thought about this, I was like, well, this is unfair. The thing is, yeah, the world is quite unfair. In this case, you cannot achieve 100% thermal efficiency. Not only can you not achieve that, the highest that you can do is bound by this equation. And the highest that you can do is dependent on the amount, or not the amount of, the temperatures that you are working with. Right? That means that, well, sometimes based on the temperatures that you're working with, you might not even get, uh, how should I say this? You might not even get a solid number for your thermal efficiency. And I have to tell you guys that for power cycles, the best we can do so far is at about 35%, 40%. In some specialized cases, we can go to about 45%, but that's pushing it, right? Even with all of the technology that we have so far, even with all of the innovations, right? Our diesel power plants, right? Sadly, those guys, the ones that burn fuel, are the ones that are most thermally efficient. They're the 35%. And in that case, if you think about it, it's so frustrating because, say, for example, your thermal efficiency is 35%. You're doing all you can. You're innovating so much. There's so many things that you're doing already to make things more efficient. 35%, right? Take it or leave it. So that's gonna be quite annoying if you're gonna think about it. And also, when you're going to think about it, that's going to help in your reality check. Say, for example, if you're gonna have a thermal efficiency calculation and it turns out to be 60%, you can already raise your eyebrows and say, maybe I did something wrong, right? And so we go back to Carnot's theorem. It says that that is the maximum, right? You might ask, well, even a Rankine cycle, is that under the jurisdiction of Carnot's theorem? Yes. So we go back to here, right? We have the input and the output of a Carnot cycle, of any Carnot cycle. And notice that in this case, in a Rankine cycle, state 1 has the highest temperature. Look at this. We can now graph a line on a TS diagram that corresponds to the highest temperature, TH. And then note that in this case, the state 2 and 3 of your Rankine cycle are the lowest temperatures, TL. And so what you can do is that now you can overlay a Carnot cycle like this and like this. Right? Notice that now what we are doing is we are looking at the two areas, right? The two pairs of areas of the Rankine cycle and the Carnot cycle. So we will then pull out these two, right? And now notice that the way we've arranged them will give us the thermal efficiency of your Rankine cycle and the thermal efficiency of your Carnot cycle. Carnot's theorem states that this is true, right? That this is true, but we're not sure. Maybe it's not, right? The thing about this work net prime, right? The one with the apostrophe here that is usually said as prime, right? The thing is, you can actually create them by just right by just separating the part wherein it's the one we know. It's the Rankine cycle network. It's the Rankine cycle heat added. Note that in this case, in both cases, in both the numerator and denominator, you are just adding some identical area. For both of them, you're just adding this gun shaped right uh area, right? And now let's just think about that and denote that as the letter A. And now what we will do, instead of a graphical kind of orientation, we will now just all put it in terms of math. Look at this, right? This is basically going to be, the left hand side is basically going to be for our Rankine cycle, and the right hand side is going to be for a Carnot cycle. In a Carnot cycle, you will always have this addition here, this area A. And so what will happen is that what we'll try to do is prove that this is correct. We will cross multiply like this, right? Notice that these two are going to go in the left-hand side. These two are going to go in the right-hand side. What we will do now is, let's clean this up. We will distribute. We'll have this, right? And notice that on both sides, you will have QA times work net. What will happen now is we can cancel those out and we will be left with A times W net and A times QA. Both cases you can cancel your A and you will be left with this, which is correct. And so that means if this is correct, okay, that means that Carnot's theorem in this case is applicable, right? It applies. And so that means it's true. Carnot cycle is going to be the perfect, the highest possible that we can do, right? So this means that for this case, right, second law is already squinting because that seems unreasonably high, right? Let's say, for example, let's give some givens, right? Let's have a high and a low temperature right here, 400 degrees and 30 degrees. So let's compute for our thermal efficiency of a Carnot cycle working under these conditions, and we will have 1 minus 30 over 400. What you will have is, in this case, it's 0.925. Right? You would say, yeah, that's right. Right? This makes sense still, but no, that's quite wrong, right? The thing about this that is quite wrong is, you remember, eta th for Carnot cycle is TL over TH. These things, both of these things, are going to be temperature readings. They are not temperature differences. You cannot just say that they are 400 degrees Celsius and 30 degrees Celsius. If you are only dealing with temperature readings, you have to make them Kelvin. And so if you're going to compute this, recompute this will lead you to 0.5497, which makes sense now because the second law is saying, you know what, never mind. This breaks, right? Or this breaks the second law via Carnot's theorem. So this is how we're going to see if a cycle that is imposed upon us that is not 100% but is unreasonably high or is unreasonably performing well, maybe it's going to break the second law through Carnot's theorem, right? And so that is the Carnot cycle, the Kelvin-Planck statement, and Carnot's theorem. Next section, we will think about the reverse, right? We will think about the Clausius statement and the reversed Carnot cycle. So I'll see you guys there. Thank you very much.